Welcome back everyone to this lecture series on polynomial regression. Let's start off with a little discussion on theory and motivation behind polynomial regression. As you know, we just completed a linear regression task, allowing us to predict future label values given a set of features. However, we didn't actually have a way to adjust or improve the model. So how can we now improve on just a linear regression model? One approach is to consider higher order relationships on the features. And there's actually two issues that polynomial regression is going to address for us. The first one is if you have a feature relationship that is nonlinear, and the second one are interaction terms between the features themselves. So let's first explore that first issue of a nonlinear relationship between a feature to a label, and how considering polynomial orders could help address this. Let's imagine we have a feature that is nonlinear. So we have some sort of x feature, and that x feature actually behaves a little more like something like log of x. Keep in mind, the log of x here, that x inside is not the feature itself. What we're here just saying is that we have some sort of feature that behaves like log of x. X inside of log is not the actual feature. This is just to denote a real equation we can follow. So we know log of x is not a linear relationship. So what do we do if we have a feature x that behaves similar to log of x? Well, unfortunately, it's going to be difficult if we just apply linear regression to a feature like this to actually find a beta coefficient that accurately grabs information from this feature, because it's difficult to find a linear relationship on this logarithmic curve. But what about the square of this feature? And hopefully this helps you with the intuition and motivation behind exploring higher orders. So if we actually take the square of this, then notice it starts to become more linear. Then we could even go to higher orders, such as the third power, and you'll notice it really starts to appear linear here compared to those original curves, which makes it much easier to find a good beta coefficient for those higher orders than the original feature. So that's essentially the motivation behind polynomial regression, is that you will be able to find those accurate beta coefficients for higher orders of the feature if the relationship between the original feature is nonlinear. Now keep in mind, we basically chose a very convenient exaggerated example where your feature behaves exactly like log of x. Not every feature is going to have relationships at a higher order, and often taking a polynomial to a very high order is going to lead to its own issues, and you may not even get useful information for the square of a feature or the cube of a feature. The main point here is to show that in certain situations, it could be reasonable to solve for a single linear beta coefficient for the polynomial or higher order of an original feature. There could be some information or signal there that you can actually grab. Let's also now consider the interaction terms. Interaction terms just means that what happens if two features are only significant when they're in sync with one another. And this is sometimes known in the business world as synergy. So for example, perhaps newspaper advertising spend by itself is not effective, but it greatly increases the effectiveness if added to an additional TV advertising campaign. For example, consumers only watching a TV advertisement will create some sales, but consumers who maybe watch a TV advertisement and are later reminded of this through an additional newspaper advertisement could actually contribute even more sales than if you had only used TV or newspaper on their own. So how can we quantitatively check if there's a synergy between multiple features, if there's actually an interaction between them that is greater than the sum of their parts? In this case, the simplest way to do that is to simply create a new feature that multiplies two existing features together to create this interaction term. We can also keep the original features. I can create the feature of the interaction term while keeping x1 and x2. So we would basically have a TV advertising spend feature, a newspaper advertising spend feature, and then a TV times newspaper advertising spend feature. And that way, we're not only considering the individual advertising spends, but also the effect they have on each other. And that's the interaction term. Fortunately for us, scikit-learn does all of this through an easy pre-processing call. Scikit-learn comes with this pre-processing library that contains many useful tools to apply to the original dataset before you actually conduct model training. For example, it comes with tools like normalization or standardization of data. And one tool it comes with is the polynomial features tool, which automatically creates both higher order feature polynomials and the interaction terms between all feature combinations. So let's actually work through a quick example of what polynomial features actually does on a real feature set. So polynomial regression is going to create the following. It will create the bias, basically a default value of 1, indicating the y-intercept term. Then it's going to create values raised to a power for each degree. So you can actually specify, when calling polynomial features, whether you want to go to an order of 2, an order of 3, an order of 4, and so on. Essentially, what exponent do you want to reach? Then it also creates interaction features between all pairs of possible feature combinations. So x1 times x2, x1 times x3, x2 times x3, and so on. Let's imagine we have a simple data set and we have two features, A and B. If we were to pass in A and B into the polynomial features where we chose an order of 2, it would return back the bias term 1, the original features A and B, the squared features A squared and B squared, and then the interaction terms between all features A and B. And obviously, this would expand even further if you started to go to a third degree polynomial or a fourth degree polynomial, and so on. The generalized terms of this would look like this. If you have a feature x1 and x2, you get 1, x1, x2, x1 squared, x2 squared, and then x1 times x2. Let's go ahead and explore an example row. Let's imagine that we have a feature x1 and a feature x2, and for a particular row, the values are 2 and 3. If we were to pass in a second order polynomial features into this row, what happens is we get back 1, the bias term, we get back 2, the original x1 feature value, then we also get back 3, the original x2 value, we also get back 4, which is 2 squared, we also get back 6, x1 times x2, which is 2 times 3, 6, and then we get 9, which is x2 squared, or 3 times 3. So now you're creating way more features from your original data set. Here we're going from 2 and 3 to 1, 2, 3, 4, 6, 9. And now hopefully we can figure out beta coefficients for all of these that actually grabs more signal from the data if there happens to be interaction term relationships or higher order relationships. Keep in mind, there's no guarantee that there are actually signals within interaction terms or higher order relationships, but you won't really know until you try. So let's explore how to perform polynomial regression with scikit-learn in the next series of lectures. I'll see you there.